Okay, so if you take a look at number 1, it wants to know which function represents exponential decay. So, I mean, honestly, what you can do is you can just go to y equals in your calculator and just graph these one at a time and just look at the graphs. Okay, so I just drew a little sketch of each one here, and if you look at answer choices 1, 2, and 3, you could all see that they're going up by a rate over time as we go from the left to the right. Whereas choice number 4 is the one that's going down, that's decaying. So choice number 4 would be our answer. Okay, number 2 wants to know which statement is true about this graph. So what I did was I went to y equals in my calculator, and I plugged this in, and I sketched a little graph of what I saw. Okay, so let's just go through the answer choices one at a time. The graph is always increasing. Well, I mean, that's your answer right there. What's happening is as you go from the left to the right, as your x values get bigger, the y values are getting bigger as well. And you can even go to your table of values and look at the y values and see that, you know, as you work your way down the graph, as the x values are getting bigger, the y values are as well. So just to go through the other answer choices, so choice 2 is definitely out, okay? The values are going up, not down. Okay, choice 3, the graph passes through 1, 0. Well, 1, 0 would be right over here, which the graph is not going to pass through. This graph actually doesn't even have an x-intercept. It actually goes through the point 0, 1. That's the y-intercept. But it doesn't have an x-intercept, so choice 3 is out. And then choice 4, the graph has an asymptote at x equals 0. Okay, x equals 0, I'm going to make a dotted line. X equals 0 would be right here. It's basically your y-axis. Okay, that's not the asymptote of our graph. The asymptote of our graph would be right here at y equals 0. Okay, the equation of the x-axis is actually y equals 0. And the asymptote, remember, is a line that your graph comes closer and closer and closer to, but never actually reaches, okay? And that's why the x-axis, or y equals 0, would be the asymptote. So choice 4 is not our answer either. Okay, so number 3 wants us to graph this on the set of axes below. All right, so let me show you how to do that in the calculator. Okay, so you're first going to go to y equals, and then if you see the math button right here, okay, you're going to scroll. I think it's faster to scroll up than down, so I'm going to scroll up until I see log base, and you can hit enter on that. All right, so we could see the base is 3, and then in parentheses, I'm going to plug in 2 minus x, and you can hit graph. You can see what the graph looks like. Okay, so this is what our graph looks like. Now, it almost appears like it stops right here, but it doesn't. We know that an exponential is going to keep going. It's going to just kind of keep going and going and going. Now, let's go to our table of values so we could decide what points we want to plot. So I'm going to hit second graph. And you're really going to just plot whatever whole number of points we see. So for example, see this right here? 1, 0. We're going to plot that. Okay. Anything below this says error, so we don't have to worry about anything down here. All right, so we're going to plot -1, 1, and so on. You're just going to keep scrolling up until you find some more whole number points here. So on -7, 2, and you're just going to plot whatever fits on the graph. Okay, so here I just kind of like drew out, or the table of values. These are the only 3 points that we could actually plot on this coordinate plane. They're the only ones that fit. And remember how we said that basically at 2 it said error, and then as you worked your way down everything was an error? That's because the x values are never actually going to reach 2. Once you hit 2, it's an error. And that tells you this is where our asymptote is going to be at x equals 2. So I like to draw a dotted line for my asymptote. So at x equals 2, I'm going to draw a dotted line. Okay, dotted line means it's not actually part of the graph, but your graph is going to approach this line, and it's just never going to reach it. So there's our asymptote at x equals 2. Okay, so then let's just plot these points. Okay, so here we go. Okay, so here's our graph, and I labeled it just f of x. If you want to write the whole equation, you can, and you could see that it's coming closer and closer and closer to the asymptote of x equals 2, but it's never actually going to reach it. Okay, now below they want us to state the domain. Now remember, the domain are just the x values that our graph is going to use. So, I mean, here, this arrow is pointing to the left. It's going to continue to go to the left and hit lower and lower x values. So the lowest x value that we're going to be at is -infinity. Okay, that's our starting point. Now, as you work your way to the right, the x values are getting closer and closer and closer to positive 2, right? Isn't this an x value positive 2? But it's never going to actually reach positive 2. So what we do is we say our ending point is positive 2, and we use a parenthesis instead of a bracket to show that this 2 is not actually included. It's going to approach 2, but it's never actually going to reach 2. All right, now it doesn't ask for the range, but I'm going to say it anyway. The range is your y values, how high and how low it goes. So your graph, right, it's going to go all the way down to negative infinity. It's going to keep getting lower and lower and lower. All right, so negative infinity would be our low point. Now, as you work your way to the left, the graph is getting higher and higher and higher. Okay, it's growing slowly, but it's still growing. The y values, right, the highest y value that we're going to use is positive infinity. It's going to continue to grow. Again, that wasn't part of the question. They didn't ask it, but I figured I'd, say it anyway. This is what they asked for, the domain. Now, the other thing they wanted was the asymptote. Okay, and we already talked about it. The asymptote is this dotted line. And the equation of a vertical line that crosses through the x-axis at 2 would be x equals 2. Okay, that right there is our asymptote. All right, number 4, they give us actually a picture of f of x, and we have to answer some questions. So letter A, what is the equation of the asymptote to this graph? Well, the asymptote we could see right here is going to be this horizontal line. Okay, the graph is coming closer and closer and closer. I'm going to make it dotted to this line right here. Okay, and we know that any horizontal line is going to have the equation y equals wherever it crosses through the y-axis at. Now, if you're not sure, this is 2 and this is 0. It looks like it's midway between, which is 1. But just to reinforce that, if you look at the equation, see how at the end of the equation it says plus 1? Doesn't that tell us that we took an exponential equation, which normally has the x-axis at its asymptote, and we shifted it up 1 unit? So if we shifted it up 1 unit, okay, this asymptote will be at y equals 1. Okay, so now in this part, they want us to state the domain and the range. The domain refers to our x values, right? Here's our x-axis. So, if you look at the left of the graph, right, doesn't the graph, keep going to the left? It's going to keep going this way forever and ever and ever. So the x values are going to approach negative infinity as we go to the left. Now, as you go to the right, even though the graph is going up, it's still going to the right. The x values, as well as the y values, but the x values are getting bigger and bigger and bigger. So the x values are going to go from negative infinity all the way to positive infinity. Now the range is how high and how low it goes. Now let's start with how low it goes. The lowest that the y value is going to reach is a height of 1, although it's not actually going to reach it. It's going to approach it. Okay, so the lowest y value that we're taking into consideration here is a height of 1. So you always put the lower number first, and then the higher number. Well, as far as the y value goes, this graph is going to continue to go up and up and up and up without any limit. So it's going to reach a height of, or I should say approach, infinity. Okay, and then part C wants to know the end behavior. So we're going to describe what happens as we go to the left on our graph, right? And then we're going to describe what happens as we go to the right on our graph. Okay, so let's start here. As x approaches, as we go to the left on our graph, right, aren't the x values getting lower and lower and lower, right? X is approaching negative infinity. Well, as x approaches negative infinity, let's talk about what happens to our y values, right? What happens to f of x? So as x goes further and further and further to the left, right, approaching negative infinity, aren't these y values approaching a height right here of 1? So we could say f of x approaches 1. Okay, now, as we go to the right on the graph, so as we go to the right, the x values are getting bigger and bigger and bigger, but aren't the y values also getting bigger and bigger? So as x approaches positive infinity, right, as we go to the right on our graph, the y values, f of x, are also going up and up and up and reaching positive infinity. Okay, number 5. Now, there's a couple different ways that you can think about this. Actually, I think I might even go over it 3 different ways. So let's see. The first way. So this says x equals 3 to the y power. Now, we know that if we were to graph the inverse of this, right, the inverse tells us you switch the x and y. So the inverse would be y equals 3 to the x power, okay? Y equals 3 to the x power. Now you could graph this in your calculator, but isn't this just exponential growth? If you have a base, bigger than 1 or 1 or greater, and you're raising it to a positive power, don't we know that our graph has to grow like this? So since this original equation is the inverse of this, we know the inverse of an exponential equation is a logarithmic equation. Okay, choice 3 is the only one that shows the logarithmic equation, the log equation, so choice 3 would be the answer. Now that might have been tricky for some of you guys to see, and if so, that's okay. I'm going to show you a different way to go about it. Okay, so let me change colors here. If I go back to my original equation, here, I'll do it over here. X equals 3 to the y power. Okay, if we want to graph this, basically we need to get y by itself. Now, to get y by itself, since we're solving for y, since it's an exponent, we know whenever we solve for y, we have to use logs. So I'm going to put the word log in front of both sides of the equation. And the reason we do that is the power rule tells us you could take your power and bring it to the front. Okay, so I'm going to have log of x equals y times log of 3. Now my goal is to solve for y, right? That way, if I have y equals, I could plug it in the calculator and just look at the graph. So to get y by itself, I'm just going to divide both sides by log of 3. All right, so these cancel. So it leaves me with y equals log of x divided by log of 3. So now I'm going to just graph. I'm going to go to y equals on my calculator and graph this and see what it looks like. Okay, now one thing I want to point out is if you plug it in like this, right? Basically exactly like we see it here. For some reason, your calculator does not like you to plug this log within a division bar. Watch what happens. If you hit graph, oh, it says error. What they want you to actually use is the division symbol. So if you go back to y equals, let me clear that out of there. So if I type in log of x, close the parentheses, and just hit divided by, and then log of 3. And then if I hit graph, it allows me to graph it. But what you could see right here is, see this graph? This, let me see if I can move this. Yep. This right here matches up with what we see in choice 3. Okay, it doesn't look like any of the other graphs. So choice 3 would be our answer. Okay, so number 6, they want us to solve this equation for x. Now, since we have an e in the equation, we know we're going to need to get this e to whatever power it's being raised to by itself. So we first want to get rid of the 148. So we could divide both sides of the equation by 148. Okay, so that leaves me with e to the 0.4x power equals, and with this you have a couple choices. I mean, you could just leave this as this fraction. If you divide this in your calculator, you do get a decimal that keeps going and going and going. So to keep your answer more exact, I would just hit math, enter, enter, and when you do, it actually takes that original fraction, and puts it in simplest form for you. So this is what I'm left with. Okay, so now that we have the e by itself, this is where you want to throw an ln in front of both sides of the equation. And the reason we do that is because if you have ln of e to some power, you're left with whatever that power was. So ln of e to the 0.4x power is just equal to this power. It's just equal to 0.4x. Okay, and I'm just going to bring down the right-hand side of the equation exactly like I see it. And if you want, you can put this in parentheses, but you don't have to. Okay, so then to get the x by itself, I'm just going to divide by the number in front of it. And when you do that, the 0.4s on the left-hand side cancel off. And you're just going to plug this whole thing in your calculator. And don't forget to close the parentheses before you divide by 0.4. And we're going to round our answer to the nearest thousandth. Okay, so when we do, we get 10.4 1, 2, 2. And there you have it. Okay, now number 7 is similar, except instead of having a whole bunch of numbers involved like we did up here, it's all variables. But there's still an e, and they still want you to solve for the exponent, so you're really going to follow the same process as what we did up here. Okay, so let's first get the e by itself. We want to get rid of this x, so let's divide both sides of the equation by x. So the x's cancel, and I'm going to bring down the e to the yt power. And then on the right-hand side of the equation, you're left with just z over x. There's nothing you could do to simplify that. Okay, so now that we have this base e by itself, we know we want to put ln in front of both sides of the equation. And the reason we do that is because when you have ln of e to some power, you're left with, that's always equal to whatever the power was. So that's going to be equal to just the power, yt. So yt equals ln of z over x. And you don't have to put the z over x in parentheses, but I'm going to. Mainly so it matches up. Look at the answer choices. They're all in parentheses, right? Okay, so we're still solving for t. We want to get the t by itself. So to get rid of the y, we just divide both sides of the equation by y. And basically, t is going to be equal to this right here, which looks like it matches up with choice 4. Okay, number 8 wants to know which expression is not a solution to this equation. So, I'm going to go about this the easiest way that I think possible. Now, if the exponent is a variable, and that's what we're solving for, we know when we're solving for a variable, as long as there's no e involved, we just use logs. So I'm going to put log in front of both sides of the equation. And the reason we do that is because the power rule tells us that if you have an exponent, you can take that and bring it in front of the word log, and then it's no longer an exponent. Okay, so again, what I did was I took this exponent and brought it in front of the word log, okay, right there. So if I want to get the t by itself, I'm going to divide both sides by what t is being multiplied by. I'm going to divide both sides by log of 2. Okay, so on the left-hand side of the equation, I'm left with just t. And then what I'm going to do, let me put approximately. I'm going to kind of round on my paper. I'm going to plug in my calculator log of radical 10 divided by log of 2. And when I do, I get approximately I'm just rounding here, 660964. Okay? Now, if I want to know which of these is not a solution, I'm just going to plug these in my calculator one by one and see which one does not also equal approximately 1.66. Okay, so let's do it. Okay, so all I did was instead of 1/2, I just used 0.5. And remember, to get to log base, you have to go to math and scroll all the way down, or just scroll up until you see log base. But I plugged these in one by one, and what you could see is the first 3 answer choices, right, are equivalent. It's the last one that's not, so choice 4 would be the answer. Okay, so number 9 gives us some information, and I'm going to underline. Remember, whenever we see the word compounded, we always want to underline that as well as what comes after it, because that's going to let us know which formula to use. Okay, so here's our compound interest formula, and we're just going to plug in what they give us. So let's see. The first thing they give us is $5,000 is placed into an account. So that's going to be our initial amount. I'm going to put that in place of the P. Okay, and then we have 1 plus. Now, if we look here, it says the rate is 3.5%. So if I take the decimal and move it back twice, it's going to be 0.035. So that's what we're going to plug in for the rate. Okay, now that's going to be divided by n. N is the number of compounds per year. So if something's compounded monthly, that's compounded 12 times a year. So that's telling us that we're going to replace the n with 12. So we have an n here in our formula, as well as one outside the parentheses. And they want to know how much money to the nearest 10 cents will be in the account after 6 years. So that's our time. That's what I'm going to replace the t with. Okay, and basically what you're going to do is you're just going to plug this whole entire thing right here into the calculator exactly like you see it. Okay, so this is, I just typed it in exactly like I saw it. And if they had said to round to the nearest cent, it would be $6,166.51, right? That 5 would have done that up to a 1. But they didn't say to the nearest cent. They said to the nearest 10 cents. So it has to end in a multiple of 10. So this is closer to 50 cents than it is to 60 cents, right? So this would be $6,166.50. So choice 4 is our answer. Okay, so number 10, we could see from this chart here, right? In the beginning of 2018, the population of Jonesville was 1,240, and its population is increasing by 6% per year, okay? Whereas Williamstown started at 890 in 2018, and it's going up by 11% per year. Now, because there's no compound interest, we're just going to use our regular exponential growth formula. All right, so let me, for right now, I'm going to leave the A equals off. I'm just going to start with the right-hand side of the equation. So let me start with Jonesville. Let me put the equal sign first. Now, the initial population, which really means the population in 2018, was 1,240. So that's what I'm going to put in place of P. Then in parentheses, we have 1 plus, and the rate at which it is growing is 6%, so 0.06. And I'm going to raise that. Normally we'd have an A here, and we'd have a T here. Raises the T power. Okay, and I just want to point out, the way I wrote this, right, this is not a function, this is an equation. If it was a function, instead of A, I would have written like A of T, or if I wanted to use a J for Jonesville, J of T. All right, now, I'm going to do the same thing for Williamsburg. It doesn't say anything about a function, so I'm just going to write A equals the population in the beginning of 2018 was 890, and then it's going to be 1 plus, the rate is 11%, which is 0.11, and that would be to the T power. Now, basically, they don't say how to solve this. Nowhere do I see algebraically. So I'm thinking kind of the easiest way to do it would be to do it in our calculator. Okay, so this is what I mean. What I did was I went to Y1 in my calculator and I typed in the right-hand side of this first equation. And I went to Y2 and plugged in the right-hand side of the second equation. Now, if I were to hit graph, chances are I'm not going to see the graph if I'm in a normal window because look how big these starting values are, right? And from there, the graph is going to grow. So like if I were to hit graph at this point, let me just hit it, right? My X and Y axes are set from -10 to +10, so I'm not going to see that. These numbers are too big. So if this is starting out at a population of 1,240 and from there it's growing, and same thing here, I'm going to need to make my Y axis huge, right? So let me go to window and see where it says Y max. I'm just going to make it a lot bigger than these numbers. Why don't I make it 2,000? And if you want to be safe, you can make it 5,000, make it something big. And now if I hit graph, I should see there's Jonesville. And let's see if they intersect. And if not, I can make my window bigger. Ooh, they do. There we go. So what I would first do is on my paper, to show work, I would just sketch a little picture of this, okay? It doesn't have to be great. But we have, let me just say, I'm going to color coordinate this. We have Jonesville, and we have Williamstown. And really what we're looking for is the point of intersection right here. So in our calculator, we know to get to the point of intersection, we go to second, trace, and then choice 5, which is intersect. Okay, now if you want to, there's only one point of intersection. If you want to move your cursor near it, you can. If you don't, since there's only one, you don't even have to. And then when we hit enter, 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 right, we hit enter until it actually says that word, intersection right here. It says approximately how many years. We're looking for the time. So we're looking for the T, which in this case is our X. So there we go. And they don't tell us what to round to. So, do they? No. Okay, so approximately how many years? I'm going to round that to the nearest year. This right here rounds to 7 years. Okay, so I just took the x value. So in approximately 7 years, both populations will be about 1,886 people. Okay, so 7 years would be the answer. Okay, now if you want to solve this algebraically, I actually think this is harder to solve algebraically, but basically what you're going to do is you're going to take this and set it equal to this. So that's what I did here. The only thing is I wrote, I just added these. 1 plus 0.06 is 1.06. 1 plus 0.11 is 1.11. Okay, now this is a little harder, I think, personally, to solve. But what I'm going to do is I'm going to divide by, it doesn't matter which one, either one of these two numbers in front. I'm going to divide by the smaller one. So I'm going to divide both sides of the equation by 890. Okay, so basically, this would leave me with, I'm not even going to simplify these, I'm going to leave this fraction as is. That would leave me with 1,240 over 890, and I'm purposely going to take the 1.06t and pull it to the outside of that fraction. Okay, so all I did was I kind of just grouped this fraction together in front of the 1.06t. And then on the right-hand side, the 890s would cancel, leaving me with 1.11 to the t power. Now, this is where this becomes a little tricky. See how they're both being raised to the t power? I'm actually going to get these on the same side of the equation. So I'm gonna take this one, and I want to move it over here. What I'm going to do is I'm going to divide both sides of the equation. And this is tricky. Honestly, the graphic way is much easier. I'm going to divide both sides of the equation by 1.06 to the t power. That way, on the left, those cancel, leaving me with 1,1240 over 890. And I know that simplifies, but I'm just going to leave it equals. Now, if you have something raised to the t power divided by something else raised to the t power, we could rewrite these as 1.11 over 1.06, all being raised to the t power, right? Because if I wanted to, couldn't I take this and distribute it kind of as an exponent on both, which would bring me back to this original step? Now, the reason I wrote it like this is because now I have one single base being raised to the t power. And when you have that, we can put the word log in front of both sides of the equation, because the power rule tells us you could take that exponent and bring it to the front of the word log. Okay, so I'm going to be left with the left-hand side of the equation. I'm just going to put that in a parenthesis. You don't need it in a parenthesis, but if you want, you can. Sorry, that's supposed to say 890. Equals t times log of what's in this parenthesis. And now, to get the t by itself, all I have to do is just divide both sides by log of 1.11 over 1.06. This is a tricky concept. This is hard to solve this algebraically. Okay, so these cancel, and I'll bring down the t. And then all you're going to do is just plug this in your calculator exactly like you see it. And when you do, you get approximately 7.2. So I guess the nearest year would be 7 years. Okay, so the bottom of this page just deals with shifts, just really knowing your shift rules. So in number 11, if this is our original function, they want to know if g of x is the image of f of x after a translation of 5 units to the left, which of the following demonstrates this? Okay, well, we know that I'm going to actually start with choice 2 and 4. If you add a number or subtract a number from the end of the function, it moves your function up or down. Okay, so this, if you add a number to the end, like this is going to move it up 5 units. Whereas if you subtract the number from the end of a function, it's going to move it down 5 units. Now, we know if we add or subtract the number within the function, right, within these parentheses here, it's going to move it left or right. And it's actually the opposite of what you would think. So if you add a number within the function, it's going to move it to the left. Whereas if you subtract a number like this within the function, it moves it to the right. So since we wanted to know which one would move it to the left 5 units, choice 1 is our answer. Okay, now number 12. If we're given this graph and we want to translate it 1 unit to the right and 1 unit down, let's think about the rules that we just talked about up here. All right, so here's what we have. Y equals log base 2. Now, I'm going to open a parenthesis in front of that x, because if we're going to the right 1 unit, doesn't that mean we have to subtract 1 within the parenthesis? And if we're going down 1 unit, doesn't that mean we have to subtract the number from the end of the function? So we're going to subtract 1 from the end of the function. Okay, now they want to know the coordinates of the x-intercept. So I'm just going to go to y equals in my calculator and graph this. Okay, so on accident I plugged it in under y2 instead of y1, but that doesn't matter. So I plugged this in and I graphed it. Now, if you can't see from this graph, I mean, it looks like to me it's going through the x-axis at 3, 0. But even if you're not sure, hit second graph, go to your table of values, and look, you'll see right here, it goes through the point 3, 0. That is our x-intercept. So choice 4 would be the answer. Okay, and then number 13. If you were given this function and we're shifting it like this, well, basically, look, 3 is being subtracted within the function. So if you're subtracting a number within the function, we know that's going to move it to the right. So this is moving it to the right 3 units. Okay, so again, we were subtracting it within the function, which in this case, within the function was within the exponent. Now here what we did was we added a number to the end of the function. If you add a number to the end of the function, that's going to move it up. Okay, so this right here moved it 4 units up. So we're going 3 units to the right and 4 units up. Okay, number 14, they really just want to know which equation is equivalent to this. Now, since this has logs and this doesn't, what we did was we used circle the base, run the race to get this out of log form. So if I take this base and circle it and run the race, right, what that means is I'm taking this base and making it the base on the other side of the equation. So this base is going to be base A, making that the exponent to the y power. So on the right side of the equation, we're going to have a to the y power. Again, when you circle the base and run the race, this becomes the base on the other side of the equation. So we have a to the y power. Now, since this base is no longer there, it's no longer holding up the word log, so the word log drops off, and all I'm left with is this x to bring down. So there's my equation. X equals a to the y power, which is, where does it say that? Choice 4, right there. Okay, x equals a to the y power. It's just in the opposite order, but that doesn't matter. So choice 4 is our answer. Okay, number 15. I see this word inverse. We know inverse means you want to switch the x and the y. So this x is going to become a y, and this y is going to become an x. Okay, so now after I did the inverse, after I switched the x and the y, now I see again, this is in logarithmic form, and these are in exponential form. So I'm again going to just circle my base and run my race. When I circle the base and run the race, basically this a becomes the base on the right side of the equation. So if the base is the a, this x is now its exponent. And then since I moved this a, it's no longer holding the word log up, so this y is just going to come right down. Okay, so this says y equals a to the x. The first one says a to the x equals y. They're the same thing, just in the opposite order. So choice 1 is our answer. Okay, so number 16, they want to know which value to the nearest tenth is not a solution to when p of x equals q of x. Now, when we see this, what we're going to do is, in our calculator, we're going to plug our first function into y1, and we're going to plug our second function into y2, and we're going to look for the points of intersection. Okay, so I plugged the first one into y1, the second one into y2, and I'm just going to hit graph, and we can see that there are 1, 2, and there'd be a third one all the way up there. All right, so let's look for the first point of intersection. I like to start with the one over here on the left. So if I hit second graph and go to choice 5, which is intersect, I'm going to just move my cursor somewhere around that first point of intersection. Okay, there we go, close enough. And then I hit enter, enter, enter. And I can see that that occurs right here at about negative 3.9. So choice 1 is not our answer. We can cross that one off. We want to know which is not a solution. Okay, so now let's do second trace and intersect. Trace 5 again. And this time I'm going to move my cursor over to the next point of intersection. Sorry if you're getting seasick. It's hard to hold all this and do the calculator at once. And then when I hit enter, 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 we could see this one is at like negative 1.1, which is choice 2. So choice 2 is not the answer. Okay. Now, if you want to make your screen bigger to see this point of intersection, I mean, you could see right off the bat, we're going to need to make our y-axis higher. So it's up to you. You can go to Window. I'm going to make my y-axis, I'm going to make the y maximum maybe 20. You could try that. Make it bigger. And now when I go to second trace, intersect, let's see if we could see that final point of intersection. Awesome, we can. So now I'm just going to move my cursor over by that point of intersection. And when I hit enter, 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 let's see, it says it's right here at about 2.05, so 2.1. So choice 3 is not our answer either. So that being said, choice 4 would be the one that's not a point of intersection. Okay, number 17, they give us a function and they want to know on which interval is the sample's average rate of decay the fastest. So really what they're telling you to use here for average rate of decay, they're telling you to use the average rate of change formula, and because it's decay, we're just going to have negative values. Okay, so this is our average rate of change formula, and because it's decaying, it just tells us we're going to have negative values. Okay, so what I'm going to do is I'm going to go to y equals on my calculator, and I'm going to plug in this function right here. Okay, and what I'm going to do is I'm going to go to the table of values, and I'm going to look at not everything on the table of values, but the numbers that are important to me. So what they want to know, again, is what over which one of these intervals is the average rate of decay the fastest. So we need, when we look at intervals like this, right, the first number represents x1, and the second number represents x2. So see on our formula how this says x1 and x2? So basically, we need to scroll down the table. I'm going to start with choice 1 until we see an x value of 1 and an x value of 10, and look at what y values correspond with them. Okay, so I'm just going to kind of slide this down. I took a picture of my work. I kind of cheated a little. So when I look at my table of values, for choice 1, I'm only concerned with the x values of 1 and 10. So now these are the two y values that correspond with them. So if I want to take these values and plug them into my formula here, I'm going to do y sub 2 minus y sub 1. So this y value minus this value. And I'm going to divide that by x sub 2 minus x sub 1. So x sub 2 minus x sub 1. Okay, again, this is x1 and x2. And then these are the y values that correspond. So if I plug them into the formula, all I'm doing is y2 minus y1 over x2 minus x1. So y2 minus y1 over x2 minus x1. And then you're just going to figure out what that's equal to. And when you do, for choice 1, you get the average rate of decay to be, technically, this is the average rate of change. So the average rate of decay would be, it's decaying by 4.06, okay? So because of the word decay, that takes care of the negative. So it's changing, it's decaying at a rate of 4.06. Okay, grams per year. All right, now you're going to do the same thing for each one of these intervals. So if we look at choice 2, right, x sub 1 would be 10 and x sub 2 would be 20. Okay, so now you're going to scroll again to the table of values. So here we go. And we're looking at the x values of 10 and 20 and the y values that correspond with them. And when we do, we're just going to take these and plug them into our formula, right? We're going to do y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And this is what you should write out when you plug them in. Okay, so again, y2 minus y1 over x2 minus x1, and this is what we get. Okay, so far, it can't be choice 2 because choice 1 is decaying at a much faster rate. Isn't 4.06 bigger than 3.265? Okay, so choice 2 already cannot be the answer. All right, then you're going to go through and you're going to do this for each of them. So I'm just going to slide this down so we could see there's choice 3. And that's what happens when we plug it into the formula. And then there's choice 4. And this is what we get when we plug it into the formula. And we can clearly see this is the biggest negative number. So this is decaying at the fastest rate. So choice 1 would be our answer. Okay, so number 18, they give us an equation here, and they say which statement accurately describes the relationship between the average rates of change of t on these two intervals. Okay, so as soon as we see average rate of change, we know we're going to be using this formula, y2 minus y1 over x2 minus x1. Okay, now these are the two intervals they give us. So in this first interval, right, here's x1 and x2. And then in the second interval, the 9,000 is our x1 and the 12,000 is our x2. So what we need to do is we need to find the average rate of change over this interval, and then the average rate of change over this interval, and then let's compare them. Okay, so there's a couple different ways you could do this. I'm going to start off with, I think, the most basic way that a lot of you guys are used to. So if you go to y1, okay, I just plugged in this equation, and what you notice is that instead of an a, right, I used an x, because that's what we use when graphing in the calculator, x and y. Now, I'm looking at these intervals. The first interval is from 6,000 to 8,000. So if you go to your table of values, right, chances are, I'm just going to hit second graph, you're nowhere near those values, right? I'm at 1, when x is 1. I don't feel like scrolling all the way till I get to 6,000. So I could do, there's a couple things I could do. If I go to, see up here where it says table set, if I go to second table set, instead of having my table start at 1 like it says here, why don't I just put it at 6,000? Okay, and then when I go to my, you know what I'm going to do actually? See how it says change in table is 1? Why don't I jump by thousands? That way it'll be super easy to scroll. So my table start is 6,000, and this just means change in table. I'm going to jump by thousands. That way when I go to my table of values, so now I'm going to hit second graph, I'm going to get to the numbers I need. So you could see when x is 6,000, this is my y value that corresponds. Now, I don't know if I need more than just that. Like, let's just scroll over to it. See how this decimal right here keeps going and going and going? I may need more than that depending on what they want me to round to. So keep in mind, if you want to see what y value corresponds with the x value, sometimes you actually have to scroll over to that y value. So for this first interval, right, it says from 6,000 to 8,000. So I'm going to need these two values, 6,000, there's my y value, and then 8,000, and then there's the y value. Now as far as this interval goes, I need to look at the x values of 9,000 and 12,000. So let me just scroll down to it. I'm going to need this x value of 9,000 with that corresponding y value. And then I'm also going to need this x value of 12,000 with its corresponding y value. Okay, so what I did was I just wrote down here the important x and y values I'm going to need, right? We're doing it from 6,000 to 8,000 in the first interval, and then from 9,000 to 12,000 in the second interval. And these are the y values that correspond. All right, if I take, right, so this for my first interval, here's x1 and x2. So if this is x1, that would be y1. And if this is x2, that would be y2. So if I plug this into my formula, right, that we see right here, I'm basically just going to do y2 minus y1 over x2 minus x1. So this is what we have here. Okay, we have y2 minus y1 over x2 minus x1. And this is what we get. Okay, now we're going to do the same thing for this next interval from 9,000 to 12,000. So if this is my x1 and x2, this would be my y1 and y2. So I could do y2 minus y1 over x2 minus x1. And when I do, this is the value that I get. Okay, so let's look at the answer choices. A comparison cannot be made because the intervals are different sizes. No. The average rate of change is equal for both intervals. Well, no, those are not equal. The average rate of change is larger for the interval from 6,000 to 8,000. Well, that's true because this is larger than that. And then choice 4 is out because it's saying that this one is larger than that. So choice 3 is going to be our answer. Okay, number 19, the value of a car depreciates over time. Craig purchased a new car in June of 2011. The value of his car, V, after T years can be modeled by this equation that they give us here. So V is the value of the car and T is the time in years. They want to know what is the average decreasing rate of change. So what that's telling us is that when we use the average rate of change formula, we're going to have, since it's decreasing, we're going to have a negative value. But anyway, when we use this formula, they want us to determine the average rate of change of the value of the car from June 2012 to June 2014. And they want us to round our answer to the nearest $10. Now, here's the deal. As far as these years go, right? Didn't they say that T is the time in years since June of 2011? Okay. So here, isn't this 1 year after 2011? So here, T would be equal to 1. And then isn't 2014 3 years after 2011? So here, T would be equal to 3. Okay, and these are going to correspond. Time is your x values. These are going to correspond to our x values. So this is really going to represent our x sub 1 as well as our x sub 2. Now what we need to do is we need to figure out what y values, or in this case, instead of a y, we're using a v, what v values correspond with these t values. Okay, so I think the easiest way to do it, in my opinion, is just to get this v by itself in this equation. Okay, well, since we have an equation that has log on one side of the equation and not the other, what we usually do is we want to try to get that out of logarithmic form. So to do that, we use our little saying, circle the base and run the race. So what happens is this now becomes the base on the right side of the equation. So if our base is 0.8, then our exponent is now that t. Okay, and now when we move this base out off from this side of the equation, it's no longer holding up the word log. So all we're left with is what comes after it. So I'm going to bring down the v over 17,000. Okay, so we're almost done. To finish solving for v, right, you can think about it like this. Doesn't this say v divided by 17,000? The opposite of division is multiplication. So if I want to get rid of this 17,000 in the denominator, I could just multiply both sides by 17,000. Whenever you want to get rid of a denominator, you can just multiply both sides of the equation by whatever's in the denominator. Because then what happens is this 17,000 on top cancels with this 17,000 on bottom, and we just bring down the v. So v is equal to, now, the way this looks to me is a little weird. You can leave it like that. You could totally leave it like that. That's technically correct. I'm going to take the number without the exponent, the 17,000, and I'm going to bring that to the front. And then that's going to be multiplied by 0.8 to the t power. I mean, you don't need, the t on the outside of the parentheses. You don't need to rearrange this. This is equivalent to this, so that's up to you. All right, now, technically, in this equation, v is acting as our y, and t is acting as our x, right? So we know x sub 1 and x sub 2 are 1 and 3. Those are our two t values. Now, we need to find the v values that correspond with them. All right, so you could do it one of two ways. You can either just, literally take 1 and plug it in for t and figure out what that's equal to, and then take 3 and plug it in for t and figure out what that's equal to. Or if you prefer, you could just go to y equals in your calculator and plug this in and look at the table of values. Okay, so this is what I mean. I just went to y equals and I plugged this in, and I just used an x instead of a t because that's what our calculator uses. Now, I'm just saying, if you were following along with me for the last example, my table of values is really messed up. Like if I go to second graph, I had set this up earlier so that it was in terms of thousands. I don't want that. I'm going to go back to table set, which is second, and then see right here the window where it says table set. I'm going to start my table at 0. So I'm going to make that as 0. And I want my table to jump by ones, not by thousands. So I'm going to come down here and change that to a 1. And now if I go to my table of values, so second graph, Now I'll see, kind of normal numbers. Now the ones we're concerned with are this one right here. When x is 1, this is moving on me. When x is 1, we're concerned with that y value. And then when x is 3, we're concerned with that y value. Okay, so I'm going to write this down. Okay, so here's my x1 and x2, and my y1 and y2. Okay, or t1, t2, v1, v2. But to use my formula here, I'm going to do y2 minus y1 over x2 minus x1. Okay, so I just wrote it out here. Now, if we subtract the numerator, let's see, that's going to be equal to negative 4,896. And that's going to be over 3 minus 1, which is 2. Okay, and then if we figure out what that's equal to, that would simplify to negative 2448. Now, we knew we were going to be getting a negative value because it says decreasing. So technically, it's decreasing by a rate of $2,448 per year. Now, they want us to round that to the nearest $10 per year. So to the nearest 10, that would be going down by 2,450, which is what choice 3 says. So there's our answer. Okay, number 20, we want to know, so this is a review. This expression is equivalent to which of the following? Now, let's be honest. It's multiple choice. If you want, you can type this entire expression in your calculator, hit enter, plug these expressions in your calculator one by one, hit enter, and just see which matches up. But I'm going to do this by hand. Okay, so a couple different ways you could start it. You could either first take this negative 1/2 and kind of distribute it onto the numerator and the denominator, but I'm going to do what I think is a little faster. I'm going to make these two terms within the parentheses into one term. Now, we know if we're dividing two terms with the same base, we just subtract the exponents. So you could either do that by hand or you can do that in the calculator, but if you were to figure out what 2 minus 1/3 is, you'd be left with 5/3. I'm just going to quickly show it for those of you that are doing it by hand. So if we did 2 over 1, right, 2 minus 1/3, we'd first have to find a common denominator. So what I'm going to do is I'm going to multiply this first fraction by 3 over 3. That way, the denominators are the same. So this would give me 6/3 minus 1/3. Okay, so 6/3 minus 1/3. So that would leave me with 5/3, right? You subtract the numerator and you keep the denominator, so that's 5/3. So basically, when I divide these two terms, it's going to leave me with x to the 5/3 power. Okay, so I have x to the 5/3 power in a parenthesis, and don't forget about this negative 1/2 on the outside. Okay, so now we know if we have a power raised to another power, we just multiply these. So 5/3 times negative 1/2. Well, first of all, a positive times a negative is a negative. And then just multiply the numerators and multiply the denominators. So 5 times 1 is 5, and 3 times 2 is 6. So it'd be negative 5/6. All right, and we have something here we don't like. We do not like negative exponents. So if we have a negative exponent, just take your expression and make it into a fraction. And then to make that exponent positive, what we do is we take the term that contains the negative exponent and we move it to the other side of the fraction bar. So since this is in the numerator, if we take this term and move it down to the denominator, well, look at that, your exponent becomes positive. And then basically, since there was a 1 in front of this x, that's my placeholder that we're going to have on the top here. So I have 1 over x to the 5/6 power. And then we're almost done. All you really have to do is, if you remember that rule that says power over root, we could rewrite this denominator as the 6th root of x to the 5th power. Okay, and don't forget about that 1 on top. So we have 1 over, and again, power over root, the 6th root of x to the 5th power. And if you look, that matches up with choice 2. Okay, number 21, they want us to determine the value of y. Okay, so here's our equation. We have this left side of the equation equals the right side of the equation equals x to the y. What you see after the comma, I mean, they have to put that there to be technically correct, but I'm actually just going to go like this. I don't want that to confuse us with what we have to do. Okay, anything that's not crossed off, that's the equation that we're solving. Now, we kind of have a lot going on the left side of the equation. So we want to work with this side of the equation. Now, first thing, see how these are in radicals? We want to get them out of radicals. So if we use our little saying, power over root, look at this first term. Isn't the 8 the power and the 3 the root? So if we were to rewrite this using power over root, this would be x to the 8/3 power. Okay, then times, now this one, if you don't see a number in the root, don't we say the square root? So there's technically a little 2 in there. So if we did power over root, it would be x to the 3 over 2 power. So x to the 3/2 power. Okay, the power is a 3 and the root is a 2. Okay, so now that's going to be over. And then here, if you have a power raised to another power, we know we just multiply those. So if it helps you, you can put that 4 over 1. And when you multiply, 4 times 1 is 4, and 1 times 3 is 3. So it'd be 4/3. So x to the 4/3 power. Okay, now let me bring down the right-hand side of the equation. All right, so we're going to try to make this all into one term. Now remember, if you're multiplying two terms with the same base, all you do is just add these exponents. So if you take 8/3 and add on 3/2, you actually wind up getting, what do you get, 25/6. I'll show you that off to the side. Okay, so I'm going to find a common denominator by multiplying this first one by 2 over 2 and the second one by 3 over 3. Okay, that way they both have a denominator of 6. So this would be 16/6 plus 9/6. And since 16 plus 9 is 25, those would add to give you 25/6. Okay, so when I multiply these two terms with the same base, I'm going to wind up with x to the 25/6 power. Okay, and I'm going to keep that over my denominator of x to the 4/3. All right, we are almost done bringing down the right side of the equation. Now we're dividing two terms with the same base. When you divide two terms with the same base, you subtract these exponents. I know this is super messy, but this says 25/6. I'm going to do this off to the side as well. If I take 25/6 and subtract 4/3 from it, I'm just going to find, in order to find a common denominator, I'm going to multiply the second fraction by 2 over 2. So that leaves me with 25/6 minus 8/6. And since 25 minus 8 is 17, that's going to give me 17/6. So to come back over here to our problem, when we're dividing these two terms with the same base, we're going to keep the base. And when we subtract these exponents, we get 17/6. And when I bring down the right-hand side of the equation, what the question wanted us to do was they wanted us to determine the value of y. Now look where the y is. If you look over here, isn't that where this exponent of 17/6 is? So y is equal to 17/6. And there you have it. All right, so number 22 says a population of wolves in a county is represented by P of T, where T is the number of years since January of 1988. All right, so the first part, what does the value 80 represent in the given population? Now, if you look at the given equation, right, we could see it follows the exponential decay format. And why I'm saying decay instead of growth is because remember, if this number is less than 1 in the parentheses, it means it's going down, it's decaying. But anyway, for part A, what does the value 80 represent? Well, 80 is in the same spot as the initial, right? P is the initial amount, the principal amount. Now the initial what? Well, the initial population of wolves. And when I say initial, I mean in January of 1998. Okay, part P, what does the value 0.98 represent in the given equation? So since this is within the parentheses, right, this number is representing 1 minus the rate. Now, if you think about this, right, this is 98%. So if you think 1 minus what percent gives you 98%, 1 minus 2% would give you 98%. Okay, so in other words, if you want to figure out 2%, you could just do 1 minus what's in the parentheses. So 1 minus 0.98 would give you 0.02, which if you move the decimal over twice is 2%. All right, so if you want to figure out what the rate is, you can just do 1 minus the number that's in the parentheses. So what this value represents is, since it's less than 1, it represents really exponential decay, right? So what's decaying here? The population of wolves. So the population of wolves is decreasing by 2% per year, really since January of 1998. Okay, so the last part C, during what year will the population of wolves be 50 or less? Now, if we look at this formula they give us, right, it says during what year, we're looking for the time. So that means we're solving for T. So if we're solving for T, we need to plug in a value for P of T. So basically for P of T, we could plug in 50. We want to know, when will the population be 50 or less? So let's just figure out exactly when it'll be 50. Let's take 50 and plug it in for the ending value, right? The P of T, the left side of the equation. And let's figure out how much time that takes. Okay, so we know we're solving for an exponent, so we're eventually going to have to use logs. But before we do, we have to get the base that contains that exponent all by itself. So let's first get rid of this 80. I'm going to divide both sides of the equation by 80. All right, so I'm just going to simplify this fraction to 5/8. And then on the right side of the equation, the 80s cancel, leaving us with 0.98 to the t power. Now that I have this base that contains the exponent on it by itself, this is where I put the word log in front of both sides of the equation. And the reason we do that is because the power rule tells us that you can take an exponent, see this exponent right here, and you can bring it in front of the word log, and when you do, it's no longer an exponent. Okay, so again, what I did was I took the exponent and brought it in front of the word log. Okay, that's what I did down here. And when I did, look at this, it's no longer an exponent. So now it's nice and easy to solve for. Since the right side of the equation says t times log of 0.98, if we want to get the t by itself, we just divide both sides of the equation by log of 0.98. Okay, so on the right side, those cancel, leaving me with t. And then here you're just going to plug this in your calculator. All right, so you can plug it in exactly like you see it. And when you do, you get approximately, I'm just going to say 23.2644. Okay, so to reach a population of 50 wolves, right? They started at 80, and to go down to 50 wolves, it takes about this amount of time, so 23.2644 years. Now, they want to know during which year is this going to reach 50 or less. Well, think about this. No matter what decimal is here, whether it's 23.8, 23.2, 23 point anything, it still happens within the 23rd year. And that's why it was important for them to say January of 1998, because we're looking at the beginning of the year of 1998. So if we take the year 1998, and since this happens sometime within the 23rd year, no matter what this decimal is, we're going to add on 23 to 1998. And when we do, we get 2021. This is the year during which the populations will reach 50 and then less than that. Okay, so Lucas, who had been saving all of his hard-earned money, decided to invest $5,000 on his 21st birthday. Lucas, having learned about how important it is to start saving early, decides to put his money into an account that grows at a rate of 3.25% per year, compounded quarterly. Now this, I always like you to underline the word compounded and then whatever follows it, because that lets us know what formula we're going to use. Okay, so if it says compounded anything other than continuously, we're going to use our compound interest formula. Now, given that Lucas does not deposit or withdraw money from the account, write a function, A of t. Now remember, when they say function, I mean, they gave it to you here, but when they say function, you just can't write A equals. You have to write A in terms of the variable we're using, which is t for time. That represents the amount of money in his account t years after the account is opened. Okay, so for this first part, they're not asking us to solve anything. They want us to just write a function. So again, they're telling us to use A of t. Now in place of P, and in place of the initial amount, the principal amount, 5,000 is what he chose to invest. So I'm going to put 5,000 there. Okay, and then we have 1 plus. Now our rate is 3.25%, but remember, to plug it into the formula, we want to get rid of that percent. So we move the decimal place back twice, which gives you 0.0325. And then we're going to divide that by n, the number of compounds per year. So if something is compounded quarterly, that means it's compounded 4 times per year. So I'm going to replace this n with a 4 as well as this n with a 4. And they want us to leave it in terms of t, in terms of the time, right? T years. Plus, if we're writing A of t, if this is a t, that has to be a t, right? Whatever goes here is what, you want to have within your formula. So the first part of the question is done. I'm going to box that off because that's something that, they wanted us to do. They wanted us to just basically write a function. Okay, now the next part says, algebraically calculate how old Lucas will be when his investment doubles. Okay, so we know as soon as we see this right here, doubles, right? We need to take whatever the initial investment was, which was 5,000, and multiply it by 2. So 5,000 times 2 would be 10,000. So we're going to plug in 10,000 for the final amount here, right, for A of t, and then we're going to solve for the time. Okay, so now we know when we're solving for an exponent, we're going to use logs. But before we can use logs, we have to get the base that contains that exponent on it by itself. So we need to first get rid of this 5,000. So in order to do that, let's just divide both sides of the equation by 5,000. Okay, so that's going to leave us with 2 equals. Now, you can either leave this parenthesis as you see it, or if you want, I'm just going to show you something real quick. If you plug just what's in this parenthesis into your calculator, it gives you this value right here. If you prefer, instead of rewriting all this, if you just want to take this 1.008125 and put that within the parentheses instead, you definitely can. The only way I'm going to say not to do that is, see how this is a terminating decimal? Terminating means it stops, right? It doesn't just keep going. If it was a decimal that kept going and going, you would know, because your calculator, I guess it holds, 10 digits with the decimal place being included one. So if it uses 1, 2, 3, 4, 5, 6, 7, 8, and then 2 more, 9, 10 digits, you know it's a value that's probably going to keep going and going, and you don't want to use a rounded value. So you could either, if it's a terminating decimal like this, you could take this whole thing and put it in the parentheses, or just leave it as is. Okay. But anyway, now we got to the point where we have the base, to the variable exponent power by itself. So now we could put the word log in front of both sides of the equation. And the reason we do that is because the power rule tells us that we can take this power and make it so it's no longer a power. You can take this and bring it to the front of the word log. Okay, so again, I took this exponent right here and brought it to the front of the word log. Okay, so that's why it's right there. Now we need to get this t by itself. So since this is 4 times t times log of this, we need to divide by log of this as well as divide by 4. I like to do it one step at a time, but that's up to you. Okay, so what I chose to do first is divide by log of this value in the parentheses. So on the right side, these are going to cancel, so I'm going to bring down 4t. And then when you plug this in your calculator, right, log of 2 divided by log of this parenthesis, you are going to have to round on your paper. I mean, I like to, as a rule of thumb, round to at least 4 decimal places. So when you do, you get approximately 85.6565. Okay, now when we do divide by 4, you want to take this entire value that's in your calculator, not the rounded value, and divide that by 4. So you're just going to literally take that value that's in your calculator and hit divide it by 4. Okay, and when you do, you get approximately, I'm still going to round to 4 decimal places, 21.4141. Now, if you go back to the question, let me just move this back up here. It says algebraically calculate how old Lucas will be when his investment doubles. So he invested this on his 21st birthday. Okay, so we want to take 21 years, how old he was, and add on how many years it takes to double. Now, this right here, it happens within his 21st year of putting it in there. No matter what the assessment was, even if this was 21.6, 21.8, it still happens within that 21st year. So I'm going to add on 21 to his original age, and that lets us know that he will be 42 years old when his account doubles. And that is our answer. Okay, and finally on to the last problem. So Nick has $8,000 that he would like to invest in an account. He is considering 3 investment options. All right, so let's see. I'm going to just kind of highlight these. Option A will pay him 2.4% interest compounded annually. All right, and I'm just going to underline compounded annually. All right, now, option B will pay him 2.375% compounded quarterly. And again, I'm going to underline compounded quarterly. I always like to underline the word compounded with whatever follows it, because that's going to clue me in as to what formula we use. All right, we have an option C. So this guy has a lot of options. Option C will pay him 2.35% compounded continuously. Okay, so I'm going to underline compounded continuously. Okay, now whenever we see compounded continuously, okay, that word continuously tells us we're going to use our APERT formula, right? So this formula we're going to use for option 3. Now, whenever we see compounded anything other than continuously, we know we can use our compound interest formula. So we're going to use this compound interest formula for option 2 as well as option 1. Well, actually, they're option A, B, and C, not 1, 2, and 3. Okay, so let's go for it. So let's start with option A. So option A, right, it says compounded annually. So we know we're going to use this formula. Now, keep in mind, I cannot just write A. If it says to write a function, right, write 3 functions. That's super important. A function cannot just be A equals. It needs to be A in terms of whatever variable you're using. Now, normally we would use time, T for time, but look at this here. They say we have to use N for time. So instead of writing A of T, I'm going to write A of N. Okay, and then equals. Now, the principal amount is going to be the same no matter what account we use. It's going to be how much he has to invest. So that's going to be $8,000. And then in parentheses, we have 1 plus the rate is 2.4%. So if we move the decimal place back twice, it would be 0.024 over N. N stands for the number of compounds per year. So if something is compounded annually, that means once a year. So I can replace this N with a 1 as well as this N with a 1. And then instead of using a T, they tell us to use N for years. So I'm going to put N right there. Now, I just want to point something out. Whenever you compound annually, you're really just using the regular exponential growth formula, which is A equals P times 1 plus R to the T power. Because think about it, isn't 0.024 divided by 1 really just 0.024? So like if I wanted to get rid of this 1 underneath there, I'm just going to rewrite that. I could have just left that as 0.024. And also, isn't 1N the same thing as just N? So really, I could have just rewritten this as just N. So again, whenever something is compounded annually, it's just your regular exponential growth formula, right? A equals P times 1 plus R to the time power. Okay, now option B. This also is going to use our compound interest formula, but this time it's compounded quarterly. All right, I'm going to write B of n, okay? We'll make an option B will be B of n. And again, because it's a function, you can't just write B equals. A function needs B in terms of whatever variable we're taking a look at here. All right, so again, the initial amount is going to be 8,000. And then we're going to have 1 plus, this time the rate is 2.375%. So if you move the decimal place back twice, that'll be 0.02375. And that's going to be divided by n, the number of compounds per year. So if something is compounded quarterly, that means 4 times per year. So I'm going to replace this n with a 4 as well as this n with a 4. And then keep in mind, instead of t for time, they want us to use n for years. So we're going to make this an n. Sorry, that decimal is crazy. Okay, so then option C, they want us to use the APERT formula, right? Compounded continuously. So this time I'm going to call it C of n. The initial amount is still 8,000. And then this time, remember, we're using this formula. So our base is E. Whenever you're working with something that grows continuously, your base is always going to be E. And in this one, our rate is 2.35%. So again, if we move the decimal over twice, it's 0.0235. And instead of using T for time, we are going to use N for time. Okay, so that first part is done. Okay, part B. So which account will earn the most money for Nick over the next 10 years? All right, so they're giving us the time. So really all we're doing is we're just plugging in 10 for each of these ends and figuring out which one gives you the most money. Okay, so if you noticed, not only did I replace these ends out here with 10s, but you have to replace these ends with 10s as well. If you wrote A of n and then replace the n here with a 10, but not that one, unfortunately, your work's not going to match up. So you want to make sure that you replace all the ends with 10s. Now from this point, the calculator does the work. You're going to plug this in your calculator, see what you get. Plug this in your calculator, see what you get, and do the same thing for C of 10. Okay, so this is what I got. Now I want to point out, the question doesn't say what to round to, but with money, when you want to find out how much an account earns, you always round to the nearest cent. Even if you're comparing accounts, those questions like how much more will account A earn than account C, over the next 10 years, the amount of money you get from account C has no impact on the amount of money you get from account A. So you would round account A to the nearest cent, account C to the nearest cent, and then you would subtract them. Okay, so with money, that's the one time that you don't just, use the entire number that your calculator gives you when comparing two accounts. You round to the nearest cent. But anyway, you could tell by looking at these numbers that option A would earn Nick the most amount of money over the next 10 years. Okay, now letter C, algebraically determined to the nearest year. I'm going to just emphasize that. How long it would take for option B to double Nick's initial investment. Okay, so let's go back up to option B. And don't look at what we did in part B, right? That's a specific year. We're looking at the original function. That's why we made these up here. So I'm going to look at this function right here. Now, if we wanted to determine to the nearest year how long, doesn't that mean we're solving for the time? So we're solving for n. So that means we need to plug in something in for B of n into the left side of the equation. Well, if we want to know how long it will take for Nick's initial investment to double, let's just double his initial investment. So if his initial investment was 8,000, if you double that, we want to know how long will it take to grow to 16,000. So we're going to plug in 16,000 for B of n. Okay, so again, all I did was I copied down option B, but I replaced the B of n with 16,000. Okay, so let's solve this. So we know that if we're solving for an exponent, right, we're solving for this exponent, we're going to have to use logs. But before we do, we have to get the base that contains that exponent by itself. So we need to get rid of this 8,000. So let's do it. Let's just divide both sides by 8,000. Okay, so 16,000 divided by 8,000 is 2. And then on the right side of the equation, these 8,000s cancel. Now, again, if you want to plug in your calculator 1 plus this decimal divided by 4, you can. But if you do that, you have to use the entire decimal that your calculator gives you. So here, I'll show you what I mean. So if I plug in 1 plus 0.02375 divided by 4 into my calculator, it gives me, let me just write this down. It gives me 1.0059375. Okay, I have to write that whole thing. I can't just write the rounded version of that. I can't just write like 1.0059, right? I have to write the whole thing. I need to use the entire thing. And if it's a decimal that keeps going and going and going and going, then leave it as is. You want to use exact numbers whenever you can. Okay, now that we have this base, the 4n power by itself, we're going to put the word log in front of both sides of the equation. And the reason we do that is because the power rule tells us we could take this exponent and bring it to the front of the word log. And then we no longer have it as an exponent. Okay, so the 4n comes to the front of the log. Okay, now what our goal is we need to get the n all by itself in this equation. So in order to do that, we have to divide by two things. We have to divide by 4, and we have to divide by log of what's in the parentheses. I usually like to divide by log of what's in the parentheses first, only for the reason, it doesn't matter what you divide by first, but only for the reason that it's one less time you have to write that big, long number. So when I divide by it here, I'm just kind of getting rid of it. Okay, so those cancel, and I'm going to bring down the 4n. And then this you have to plug in your calculator. Now when you do, you're going to get an irrational number that keeps going and going and going. So unfortunately, if we're going to round down our paper, I like to at least round to 4 decimal places. But when we divide by 4, right, because we have to get rid of this 4, you want to divide that entire number that's in your calculator by 4. Okay, and when you do, you get approximately 29.2717. So that's the time it takes for Nick's initial investment to double. Now, they just want us to determine to the nearest year. So they're just asking you, not like during what year it happens, how old he's going to be. We don't know any of that. They just want you to take this number and round it to the nearest year. So to the nearest year, that would round to 29 years. Okay, and then finally, algebraically determine to the nearest tenth of a year, how long will it take for option C to increase Nick's initial investment by $4,000? Okay, so since this was on the previous page, I just kind of rewrote it here. So this is option C. Now, if we want his initial investment to increase by $4,000, well, he invested $8,000, right? Let me just do this off to the side. He invested $8,000. So if we want that to increase by $4,000, we want to know when will he have $12,000 in the account. So we want to know when will the final amount, or how long, we're looking for the time, will it take to reach $12,000. So what I'm going to do is I'm going to replace this C of n, the left side of the equation, with 12,000. And then we're going to solve. The equations that contain E are actually the ones that are a little faster to solve. Now, since we're solving for an exponent, and we have a base of E, we need to get this E to this power by itself, and then we know we use ln to get rid of an E, right? Okay, so let's first get rid of the 8,000. Let's divide both sides by 8,000. And 12,000 divided by 8,000 is just 1.5. And then what happens on the right side of the equation is the 8,000s cancel, and it leaves me with E to the 0.0235 n power. Now again, to get rid of an E, all we have to do is throw an ln in front of both sides of the equation. Okay, so I'm going to bring down the left-hand side of the equation, and then we know that ln of E to any power is just equal to whatever that power is. Okay, a lot of you guys like to think about it as the ln cancels off with the e, but really ln of e to this power is equal to that power. All right, so we're almost done. To get the n by itself, we just divide by the number that's in front of it. Okay, so those cancel, leaving me with n. And you're just going to plug this in your calculator. And when you do, you get approximately 17.2538. All right, so let's look back, and it says they want us to just take this and round this to the nearest tenth of a year. So nearest tenth is 1 decimal place. Now, if we look at the number after it, if it's 5 or higher, we round that up. So that's going to get rounded up to 17.3 years.